Hello everyone, today let's take a look at Quantipus number 66, another combinatorics question where we have a collection of 6 distinct coins with these values right here. So it's asking us how many different total amounts of money can we form. So I drew out a picture of what the question's asking. Here's our 1-cent coin, here's our 5-cent coin, all the way up to this being our 100-cent coin. So one way I could form a total amount of money is, let's say I chose this coin and this coin and this coin, and then I'd have 61 cents. So that's one way of doing it. And then if I also added in the 5-cent coin, then I'd have 66 cents, and this would be a different way of choosing a total amount of money. So first of all, let's just note that each coin is going to be greater than the sums of all the coins before it. For instance, this 10-cent coin is going to be greater than the 6 cents before it. The 25 cents is going to be greater than the 16 cents before it. The 50 cents is going to be greater than the 41 cents, etc. And that kind of gives us the property that we'll say we have 66 cents here, right? We've chosen the 4 coins in green. Well, there's no other way to get 66 cents other than choosing these 4 coins. Therefore, because each subset of coins gives us a unique total amount, we just need to calculate the number of unique subsets. Now, there's 2 ways to think about calculating the number of subsets, which are both going to relate to part B. Before we do that, let's just first note that we need 1 or more of these 6 coins to be in our subset, right? We can't have the empty set. We're not including that in our total just because the question said so. So the first way to think about it is with combinations. So how many subsets are there first with 1 coin? Well, we have 6 coins. We're choosing one of them, so 6 choose 1. Now let's add in the number of subsets with 2 coins. So we have 6 coins. Let's choose 2 of them. Now let's add in the number of subsets with 3 coins, etc. The number of subsets with 4 coins, 6 choose 4. So this is going to be our final answer, where this is 6, this is going to be 15, this is going to be 20, 15, 6, and 1. Now again, the reason that we didn't add in 6 choose 0 is because we need at least 1 or more of these 6 coins, right? We can't deal with the empty subset. And when you end up summing all these, you get 63. But now there's also another way to think about it. So let's look at way number 2. We can think of it like basically each one of these coins has 2 options, right? Either it's included in the subset or it's not included in the subset. And I can basically make subsets in this way as well. For instance, look here, these are my 6 coins and I'm choosing to include this first one, exclude the 5-cent one, include the rest of them, right? Or for instance, I could exclude the first one, include the second one, exclude, include, 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 and that would correspond to 1 being excluded, 2 being included, 3, this one's excluded, and then these 3 are all in it, and that would correspond to a sum of 180. So now how many ways are there for me to make subsets like this? Well, I have 6 coins, and for each one of them, I have 2 options, include or exclude. So I have 2 times 2 times 2 times 2 times 2 times 2 options. So that's obviously just going to end up being equal to 2 to the 6, but wait a minute, we do not want to include the one case where everything is excluded, right? Because that would be the empty subset. So we just want to subtract off the cases with all e's. How many cases are there with all e's? Well, there's only going to be 1. There's only one way to choose the empty subset, so let's just subtract 1. 2 to the 6 is 64, so minus 1, you're going to get 63 as well. So you can see that these are equal here. Now, can you see how this is related to part B? Well, let's look at part B now. So for part B, this is what we want to show. So in part A, we kind of saw a real application of this, right? The 2 different ways of thinking about it. So how do we actually show this? Well, back in Quantipus 39, we had a little hint as to how to do it. Basically, let's take this right here. Let's take x plus y to the power of n. We know from previous problems and the binomial theorem that this is just equal to, in the expanded form, k equals 0 to n choose k, and then we're going to have x to the power of n and y to the power of n minus k. So we do the same thing we did in 39. We just set x and y both equal to 1, and that's going to kind of kill these terms, because when x and y are both 1, it doesn't matter what power you raise them to, they'll still be 1. And then when we do that on this side of the equation, x and y are both going to be 1, so we're going to get 1 plus 1, which is 2 to the power of n, and that's just equal to this right here, which is exactly what we wanted to show. So that's how we use the binomial theorem to prove this identity right here, and this is how we can actually think about it intuitively applied to a real problem like we did in part A.